Thank you. Hi, I'm Jacqueline. I'm just recently graduated from the University of Iceland, and today I will be giving you a bit of an overview about physical processes that we observed during the Fagradalsfjall Fires, so the 2021 and 22 eruptions that happened in Iceland. So first, a bit about the Reykjanes Peninsula. As most of us probably know, Iceland is the combination of a mantle plume and also the continuation sub-area of the Mid-Atlantic Ridge, and it actually surfaces right in the Reykjanes Peninsula over here. And over here, you can see the Reykjanes Peninsula that is further classified into several volcanic systems, 7 to be precise. And in terms of eruptive history, there is a cycle that usually keeps going during the for the Reykjanes Peninsula, basically, whereby you have approximately 300 years of activity, followed by 800 years of quiescence. And during these 300 years of activity, you usually have a lot of basically events that keep going on for decades within one system, usually starting out in the east, and then they move on west within the peninsula until then they stop and you have 800 years of quiescence. And in fact, the last eruptions that happened were the Reykjanes fires 800 years ago in the 1200s. And the ones that happen now basically are following up over that. And there has the fact that we have 2 eruptions now that confirms that a new eruptive period is now going on in Reykjanes. So a bit of information about the 2 eruptions first. So the Geldingadalir eruption was the first eruption that came up, this one in 2021. It lasted 6 months, from the 19th March until 18th September. It started with one vent over here, the southernmost one, and it was mostly having fountaining activity over there, bubble bursts and that sort of thing. And then on the 5th of April, a second vent opened, the northernmost one up here. And then between the 5th and the 13th of April, all the other vents opened up in between. And basically by the time it was end of April, it had all the activity was confined towards vent 5 in the middle, and that continued towards the end of the eruption. The lava flow that was created, seen here in red, was approximately 4.85 kilometers squared and produced a volume of 0.15 cubic kilometers. And it emitted approximately 4,000 to 5,000 in terms of sulfur dioxide daily. In terms of, that was obviously the largest of the 2 eruptions. Then Meradalir came by in 2022, so very recently, and that one lasted 3 weeks in August. You can see it here delineated in yellow. It was way smaller. It also was a fissure eruption, and similarly, it confined eventually into one vent. The area was approximately 1.16 kilometers squared, and then the volume was approximately 0.01 kilometers cubed. But enough about the chronology. What was very interesting about this eruption was, firstly, before the eruption even started, our group was able to confine the area that was most likely to erupt before it even started erupting. Over here in the middle, what you can see are susceptibility maps, short-term susceptibility maps that we created. And we did this by combining long-term susceptibility based on geological data, so eruptive histories and things like that, along with 2 days worth of the most recent seismic activity, so tremors. And like that, we were creating short-term susceptibility maps that tell us where, at that specific point in time, we were most likely to have an eruption. And as you can see, by 10th March already, it was starting to focus around the Fagradalsfjall region. Based on that, we were able to also then input these results in QLava and try and decide the area where it was most likely to flow once the eruption starts. And in fact, by 17th March, this is what we had produced by 17th March, we had already gotten quite an accurate representation of what we were to expect in Fagradalsfjall, because once we constrained the area, the unique geology of this specific part of Reykjanes, which is like a lot of bowl-shaped valleys, allowed for, like, once you know the area, then obviously there's only one way, which is to fill the valley. So it was much easier for us to get accurate results. And it was very easy to do this even in cars. It's a very lightweight model, so very useful for future eruptions as well. Yeah, and now in terms of chronology as well and vent activity. So starting first with the 2021 Geldingadalir eruption, we decided to split such a long event into 3 different stages, and then each stage would have phases and episodes. And the way that we delineated this was that a stage would indicate a particular type of vent activity, and a phase within it would indicate a slight change in periodicity with in terms of how long between pulses that what we're observing, and then an episode would be just the time frame within which you would have a few minutes of activity followed by a few minutes of break, and then it repeats itself. So based on that, between 19th March and the 1st May, that's the first and the longest stage, it had 6 phases, no episodes, it was very continuous. So it had weak but very continuous fountaining. It was mostly strombolian and a lot of bubble bursting that we observed, as you can see in the image below. Then stage 2 followed, and this is when the weak fountaining started becoming more intensive, but as a result, it introduced also episodes. So I started seeing breaks in between each episode, and therefore, for most of the rest of the eruption, we had 11 phases, over 7,000 episodes, and these were intense, and especially in May, the fountains were sometimes reaching up to 200 meters in height. Finally, stage 3, it was just the last week of the eruption. The activity quieted down. It was mostly steaming, as you can see over here, and just tiny bubble bursts. There were circa approximately 30 episodes, and yeah, basically that was pretty much it. And then the eruption ended. As for Meradalir eruption, there weren't that many changes that were observed. Obviously, it was also much shorter. So we defined it as one stage, and it pretty much had no episodes. It just had continuous and weak fountaining that was observed, basically. Also very interesting is that the Fagradalsfjall Fires in total had pretty consistent chemistry, 7.5 to 8.5 weight% in terms of magnesium, and the magma discharge was very constant within the respective eruption. So you had 12 meters cubed per second, as you can see here, and then slightly less magma discharge for the second one. But despite the fact that these 2 conditions were very constant, we still observed a wide range of lava morphologies. You can say the full spectrum. As you can see, we have spiny, ropey pahoehoe, like rubbly, and this is actually the most common. We had rubbly pahoehoe that seemed to be transitioning to and also the at the margins. So it was mostly all these different types of morphologies, and we think that means that basically the thermal budget, the slope, and the local fluxes were actually the ones controlling these morphologies that we're observing here. So now we have a nice video that you can observe whilst I talk. So in terms of lava pond dynamics, for 2021, so both of them had ponds and both of them had specific pond dynamics that were observed. For 2021, as you can see, the lava looks very runny, and the reason is because it was very well insulated and it was constantly degassing. There were regular breakouts, but not of huge volumes, and it only had a final drainage and a collapse of the pond itself, like towards the last week, so in stage 3, that last week of the eruption. And yeah, basically as a result of that, the only way it was kind of moving was through these crust recycling that you're seeing here in this video. As for 2022, the lava, oh, it's not, okay, it's not loading for some reason. I'm so sorry for that. Basically though, it's, as you can see, you can see where it's breaking into. So that's a breakthrough that continued flowing. But yeah, the lava in this pond held up specific ramparts. You could see them going inwards into the pond. And you had much more frequent drains or breakthroughs, we were calling them, as you can see here, like an entire bit of the rampart would just collapse and it would just drain the entire pond. And yeah, we were noticing that the ramparts would also start collapsing, and that it was basically the pressure of the liquid lava that was keeping up the pond's shape. Yeah, and then another very interesting feature that we observed was we could not observe it real time because, as you can see over here, the event happened very far away from the actual vent. So the vent would be in that area, and here, this is where everything was happening. And all the cameras for real-time monitoring were all pointing towards the vent activity. So, and it was also bad weather. So we only noticed this once once we arrived back after it had already happened. But based on LiDAR surveys that we did via drones, we noticed that something very interesting had happened, which was basically, I'm going to explain over here. There were two off fronts that were flowing over here and over here from the 2022 eruption, and they were flowing onto the 2021 lava that was right underneath it. And was the first front became stationary, the second one continued advancing. On doing so, the cumulative weight pushed onto the 2021 lava and squeezed out still molten lava that was from 2021, and this re-erupted over this region, also in this region, and continued all the way here. And in fact, it was only because the liquid 2021 lava infilled spaces within the first front that we know that it was stationary. And the reason we know the second one was not, and that it was still advancing, is because after the 2021 squeeze out was in place, the front literally bulldozed onto this 2021 lava and turned it into rubble, and re-squeezed out some more things that were basically, a part was bulldozed and a part was just normal ropey pahoa. And it was very interesting because you could also see that even their crystal content was different, and that's how we originally noticed that one was 2021 and one was 2022 lava, because the 2021 tends to have a bit more olivine content. And yeah, for more information about this though, you should go to the poster sessions that are about to start after my talk. And my colleague, Lydia, will be giving a more in-depth discussion and presentation about this. And yeah, as a summary, the Fagradalsfjall Fires have been extremely significant in that they have indicated there's a newer eruptive period that has started. So now we have a few decades, if not centuries of eruptions. And yeah, we found that we could apply lightweight interdisciplinary models, and that's always good, especially for risk management. And it was also a very convenient location, and as a result, because of the nice structure of where it erupted, it allowed for quasi-real-time coverage. And for both vent activity, lava pond dynamics, the squeeze out that I mentioned, we also observed incipient rootless eruptions, and it helped us define a bit more the relationship between the flow morphologies and the eruptive processes. Yeah, that's all from my end. Do you have any questions?